So the next thing we have to cover is implicit differentiation. So what does that mean? So far we've been deriving things. We've been deriving functions that are y equals, I don't know, like 4x plus 7, right? It's 1y, and then everything else, the equation is on this side, right? We have f of x equals whatever. But what do you do if you have to derive something like a circle, right? If you have y squared plus x squared equals 16, right? If you have a circle equation. If you're trying to derive this, how would you derive the y and the x if they're both together? That's what implicit differentiation is. It's when you have an equation with y's and x's and they're together, and how would you derive it? So if you have y to the fourth plus 3x squared equals 6y plus 18, right? And you had to derive this, and you had to find dy over dx. And dy over dx is the derivative. So when you derive x values, for example, if you have like 2x, right, and you're deriving it, d over dx, right, is what you're applying to it. If you derive this, you get 2. And that's it, right? Because this is in respect to x. It's d over dx, right? You're looking for it in respect to x, so that means that x is like what you're deriving. If you're deriving y's, if you have 2y, d over dx, since it's in regards to x here, if you're deriving it, you get 2, but then the y is not just going to go away like the x did. It's going to go on top of here and go dy over dx. So anytime you're deriving a y in respect to x, you have to add a dy dx over here. The reason why that doesn't happen with x's is because if you add a dx over dx, this is just the same thing over itself, so this is just 1, right? So this does happen, but it goes away, like it's not important. So whenever you derive a y, you derive it normally, but you multiply it by a dy dx. I'm gonna give an example to make this make sense. Let's say we have the equation 2y to the third power minus 15x squared equals 6y plus 13. So let's go about it using implicit differentiation that we just learned. So y, when you're deriving it, you derive it the same way as normal. You bring the 3 down and subtract 1 on the exponent, so you get 6y squared. But then you gotta apply the dy dx, right? Because it's deriving in regards to x, and it's a y value. So 6y squared dy over dx minus, you derive the x like you normally would, 30x, equals 6, derived as normal, but add a dy dx, and then plus 0. So when you're deriving something, you're trying to find the dy dx, you're trying to find the slope. So just like any algebra equation, you have to get the dy dx by itself. So to do that, we're going to move all the dy dx's onto the same side. So we're going to subtract this value and bring it over here to the right side. So if we do that, we're left with negative 30x equals 6 dy dx minus 6y squared dy dx. And then if you're trying to get dy dx by itself, you factor out the dy dx onto both of these terms over here, right? And that'll give you negative 30x equals 6 minus 6y squared dy dx. And then you're so close to having dy dx by itself, treat it like a variable. So what you want to do is divide both sides by 6 minus 6y to get it by itself, and you'll end up with negative 30x over 6 minus 6y squared equals dy over dx. And you have your dy dx, you have your derivative by itself. So this is the derivative of this function up here. So all you do in implicit differentiation when you're deriving things with x's and y's is you put a dy dx anytime you derive a y, if it's in respect to x, and then get the dy dx by itself, factor it, and then divide it by whatever you factored out, right? We'll look at one more example, and then we'll look at how to apply this. Okay, I have one more problem up. Go ahead, pause it, solve it. Let me put parentheses so it makes sense. Boom, boom. Go ahead, solve it. Alright, cool. So you derive it like you normally would. 7x4, 7 times 4 is 28, x to the third power plus 13, and then it's a y here, so dy dx equals 8 times 3, 24, y squared, but it's a y, so dy dx plus 9. And like before, you want to get all the dy dx's over to one side, so I'm going to move the 9 over, and I'll move the 13 dy dx over to the right. So we're going to have 28x to the third minus 9 equals 24y squared dy dx minus 13 dy dx. And then again, we're going to factor it. So 28x to the third minus 9 equals 24y squared minus 13 times dy over dx. And then, like before, we're going to divide it. 28x to the third minus 9 over 24y squared minus 13 equals dy over dx. So it's the same steps as well. You're deriving everything, having the dy dx's, moving on to one side, factoring, and then dividing to get your dy dx function or your derivative function. I'm going to show you how this is useful and how you have to apply it on the exam. Okay, so an example of when to use something like this is when it gives you an equation and it tells you to find the horizontal tangent lines of a function. So let's break this down. The horizontal tangent line, right? So a tangent line is the instantaneous rate of change or the slope at one point. And if it's horizontal, that means it's a completely sideways slope line. So that means when the slope equals 0, it's asking you to find the equation, right? Because if 0 slope, this is horizontal, this is a horizontal tangent line. So it would be something like this, right? At this top here, there's no slope because it's just straight flat. So it's asking you to find this equation of the tangent line at that point. In pre-calc, we learned point slope form, which is y minus y1 equals m x minus x1, right? This is the formula to find an equation of a graph, right? So the first thing we have to do if we're trying to find the equation of the tangent line is find out what the y1 value would be, what the x1 value would be, and what the slope would be. So to do that, the first step is to derive it. If we derive this, we use implicit differentiation, we get 8x plus 4y dy dx equals 0. And then we'll move the x over, 4y dy dx equals negative 8x. And then we'll derive it both sides by 4y, and dy over dx equals negative 8x over 4y. Or if we simplify this, we'll get negative 2x over y. Now, if our dy over dx equals 2x over y, right? And we're trying to find our horizontal tangent line. So we're trying to find the point where the slope equals 0, right? So we're trying to find the point where this equation, this slope formula equals 0. So how would we do that? We would have, the top would have to equal 0, right? So 2x would have to equal 0 because it would be 0 over y. And 2x equals 0 means x equals 0, right? Because 0 times 2 doesn't change. So we know that the x value is going to be 0. So the horizontal tangent line is going to happen when x equals 0. Now the next thing we have to do is we have to find the y value of where that would be, right? And to do that, we just plug x into our original equation, because when x is 0, we're just going to be able to find out what y is if you just look at our original equation. So if you plug in 0, we get 0 plus 2y squared equals 18. We can divide both sides by 2. We get y squared equals 9, y equals 3, plus or minus 3. Because you're square rooting both sides, right? So y equals plus or minus 3. So you know there's going to be two horizontal tangent lines here at y equals positive 3 and y equals negative 3. So your answer is, you would have a horizontal tangent line at 0, 3 and 0, negative 3. If you wanted to plug everything back into the equation to write the actual tangent line, it would just be y equals negative 3 and y equals 3. Because our m in this case is 0 because of horizontal tangent line. So everything on the right side is going to equal 0 because it's 0 times the x values. So our y value here is 3 at negative 3. So it would just be y equals negative 3 and y equals 3. So you can move it over. That's it for implicit differentiation. It's pretty important, but it's a little bit hard. We're moving on.